Welcome to Module 202B on Series Resistive Reactive Circuits. We're going to be looking at both Series RL and Series RC circuits and how they behave. This module has four objectives that we're going to split into two videos. The first video is going to cover the resistor and an inductor in series, and the second video is going to cover the resistor and the capacitor. So let's get started with part one on Series RL circuits. Series RL circuits are any time that we have a circuit that has both inductive and resistive components placed in series with each other. We find this with any type of inductor that we have. Since an inductor is a coil of wire, the wire provides the resistance, whereas the coil provides the inductance. So every inductor is really a series RL circuit. Since my series RL circuit has two different components, I have to think about how those two interact with each other. Both the resistance and the inductance will affect current in a different way. With resistance, it is a direct opposition to current, so therefore when we look at our phasor diagrams, we find that a current is going to be on our reference line, and that is because our current is our constant. And our voltage for our resistance is going to be shown as in phase with the current. Since my XL component is in opposition to the change in current, we find that it is a lagging circuit because it's inductive, and therefore on my phasor diagram it has to be shown to be 90 degrees lagging to my current. Since my current is on my reference line, that will place my voltage for my XL on my positive 90 degrees. When it comes to my total voltage, even though that we know my total voltage is 120 volts, it's not going to be on either the 0 degree or at the 90 degree, but it's somewhere in between. We have to consider the vertical component of the XL and the horizontal component of the R, and it's the interaction of those two that gives me my voltage total. Therefore, my phase angle is going to be dependent on the values of VR and VXL. Another way to look at this is to look at the impedance triangle. If I take this circuit where I have an XL of 60.3, I would show that in a vertical form. And I'd take my resistance, show that on the horizontal. With a resistance of 100 ohms, an inductive reactance of 60.3 ohms, I can use my Pythagorean's theorem to figure out my total impedance is going to be. In this case, my total impedance is 116.7 ohms. And I can also take my resistance and my impedance and use my trigonometry to figure out what my phase angle is going to be. So I know that this circuit operates at a 31 degree phase angle. Keep in mind that phase angle also refers back to the voltage. So it is a 120 volt supply operating at a 31 degree phase angle. Now that I have my total Z, I can use my Ohm's law in order to calculate what my current is going to be. So my current is going to be 1.028 amps for this circuit. Remember that current is constant, so therefore that's 1.028 amps for both the resistance and the inductive component. Since my current is a constant, I can use that current against every single component in my circuit. So if I wish to find out what the value of VR is, I can simply take my current, multiply it by my resistance. The same thing for my value of VXL is I take my current, multiply it by my XL, it will give me VXL. And of course, I times Z, which should give me my total voltage. Another way to figure out our voltage values is to use our phasor diagram and trigonometry. Since we know that our voltage is 120 volts at 31 degrees, we can figure out what our VR is by using the cosine. The formula for this would be VR is equal to E times the cosine of theta. In this case, 120 volts multiplied by the cosine of 31, which gives me a value of 103.2 volts. That's the same as the horizontal aspect of my voltage triangle. VXL, since that is my vertical aspect, would use sine. Same formula, except for instead of cosine, we're going to use sine. So E times the sine of theta. In this case, 61.8 volts. Now we've completed our phasor diagram. We can see our in-phase component, we can see our out-of-phase component, and we can see our circuit total. When it comes to our impedance diagrams, as well as our phasor diagrams, as well as our power diagrams, they should all look exactly alike. The other thing that will be exactly alike is the phase angle. And remember, my power factor is the cosine of my phase angle. When it comes to our power triangles, we do have three different components we have to consider. We have our apparent power S, which is our total overall power consumption. We have our true power P, which is our resistive component. And we have our reactive power Q, which is our reactive component. When we're solving for these, we can still use our power formulas. However, we have to make sure that we use the components that are in the same line as everything else. For example, for P, I can use my I squared since my current is constant, but I must multiply it by the R to get my total P value. I can also use the voltage of my resistance squared divided by R. So anytime I'm trying to figure out something for power, my true power, I have to use the values that are on that horizontal component. The same rule applies whenever I'm looking at the reactive power. Anything that I want to figure out for Q, I have to use my XL values, which that means XL and VXL, or I. Once again, I is my constant. When I want to figure out my apparent power, I have to use anything that is on the hypotenuse. This includes my total voltage as well as my total impedance. Now that we have an understanding on how to solve RL circuits, now it's time to put that knowledge to the test. If you want to review this video, now is a good time to pause, go back through the information until you know that you got a good handle on it. If you're confident in your abilities, let's solve this circuit. This looks just like the ones that we've been doing before. However, this is an inductor that is under the same core, and the two lines above those two components show that they're both part of a coil. Instead of our XL, or inductive reactance, I've just given you your inductance. So your first step is going to be calculate your XL. Pause the video here, and I want you to solve for this circuit. I want you to get your impedance triangle, I want you to get your voltage phasors, and I want you to get your power triangles done. Once you have those complete, resume the video and we'll walk through it together. Okay, so as I mentioned earlier, my first step is to find my inductive reactance, my XL. So I'll use my formula XL equals 2 pi FL and get a total inductive reactance of 9.425 ohms. Since I have my XL and I have my R, I can now go ahead and do my impedance triangle. My impedance triangle using Pythagorean's theorem will give me my total impedance of the circuit, being Z equals 17.043 ohms. The other piece of information I can get from my impedance diagram is also my power factor as well as my phase angle. So our power factor in this case is 0.83, and all I did to find that was take my R and then divide that by Z. Now that I have my total impedance, I can take Ohm's law again, divide 120 volts by my 17.043, and I end up with a current of 7.041 amps. Remember that my ampacity in a series circuit is my constant, so I'm going to be using this number in a number of different formulas from here on in. Now that I have my ampacity, I'm going to figure out my voltages. I need my voltage for my resistive component, and I need my voltage for my inductive component. I already have my total voltage, so I'm not going to worry about that. I'm going to use my I times R in order to get my VR, and I'm going to use I times XL in order to get VXL. Remember, I have to use the component on that line to solve for that. So the voltage of my resistance, I must use my resistance. The voltage for my inductive reactance, I must use an inductive reactance. Our next step is to figure out our power triangle. Remember once again that our power triangle and our impedance triangle should look exactly the same. They have the same phase angles, they have the same proportions. My formula for figuring out my power is going to be my power formulas, but once again, in order to figure out what I need for my true power and my reactive power, I have to use my resistance and my inductive reactance. In order to get my total apparent power, I simply go E times I to get 844.92 VA. In order to get my power, I'm going to use my current, because my current is my constant, I can rely on that. My current being 7.041 squared times my resistance of 14.2 will give me total power of 703.818 watts. For my reactive power, I'm going to use my reactive component, and once again I want to use my current, my constant. I squared times XL, 7.041 squared times 9.425 gives me total reactive power of 467.25 bars. When I put these into my triangle, I can double check my math by applying Pythagoras' theorem. They should come out within a couple decimal points. So that's it. That is my solution for this circuit. I have my impedance triangle, so I know what my total impedance of my circuit is. I have my total amperage, which I can double check with my meter. I would know the voltage of my resistive and my inductive component within the coil. There's no real way to test that voltage, of course, because it's built within that coil, but at least I have numbers to support what I have. I'm able to figure out what my operating angle is, as well as my power factor, and I can figure out what my different power components are going to be. And my power components can be measured with a wattmeter. And my circuit is done. If you didn't understand how I got to certain things, feel free to write me or go through this video again to see how exactly I did things. If you understood the last one, we're going to move on to one that's a little bit more challenging. In this circuit, I have an inductor which has resistance and impedance together within it, and then I also have a separate resistor. So we're going to break this down a little bit different. You can pause the video now and see if you can tackle this. Remember that all my resistances, being at the same angle, can be added together. That's your hint. Go ahead and try to break this down. Now that you've had a little bit of time to try to solve this one for yourself, let's go through this one together. Remember that organization is key to keeping your mind clean. So make sure that your worksheet is organized and all your numbers are in a logical place so you can look back at them and figure out if you've made a mistake somewhere. I'm going to show you a little bit of a different way to organize this particular problem that works better for me, and if you want to use it, that's great too. Just like in the last problem, I gave you inductance instead of inductive reactance, and so once again, our very first step is going to be to solve for the inductive reactance. So I have an XL value of 31.29 inside that coil. Now keep in mind, I do have two different components here. I have a resistor, and then I also have a coil. So that coil I want to kind of treat on its own. I want to create different columns for each one of my devices. So I'm going to have a column for my resistor, another column for my coil, and a third column for my circuit total. That way I can keep everything nicely organized and I can see whatever I want. Once I have my columns organized, I want to draw my triangles that represent what the different components are as well. These triangles represent not only my impedance triangles, but also my power triangles, and will also reflect what's happening with my phasors. Once I have my triangles in place, I can now put on the known values that I have. So I know what the resistance of my resistor is, 25.8 ohms. I know what the resistance of my coil and also the inductive reactance of my coil, so I can put both of those values in my coil slot. And you'll notice that my XL for my coil is the same XL in my circuit total. That is because that is the only inductive reactance in my circuit at all. So that just goes straight across. If I had two coils, then I'd want to add both inductive reactances together in order to create a larger value. In this case, my only XL is the XL that I have for my circuit total as well. When it comes to the resistances, I can simply add the resistances together to get a total resistance of 36.1. So I just took the value of my resistor and then the resistive value of my coil and put them together. So all horizontal components add up together, all vertical components add up together. The only thing that is left is for me to find my Z. I need to find the Z of both my circuit total and my coil. The Z of my circuit total is going to give me my ampacity. The Z of my coil is going to give me my voltage drop across the coil. So they're both important numbers to get. Both these values are ones that I can measure with my meter as well. So the Z total for my circuit is 47.773 ohms, where the Z of my coil is 32.942 ohms. Now I'm done with my impedance triangles for this. I have to move on to both my voltages and my power. So I'm going to move down the page a little bit and do the next part of it. Keep in mind that now that I have my Z total and E, I should find my current, because then I'm going to need my current to figure out everything else when it comes to power and my voltage drops across all my components as well. So in this case, I have 120 volts. I have a Z of 47.773, and using Ohm's law, I'm going to have 2.512 amps. Now that I have my total current, I have to realize that current also applies to everything else inside the circuit. So that is the current for my resistor as well as for each component inside my coil. It's very important in a series circuit to find your ampacity. That is my constant, and that's the one I need to do. Once I have my ampacity, now I can use Ohm's law again in order to figure out what the voltage drop across each one of my components. The way we're going to do this is we're going to solve all my resistive voltages, then all my inductive voltages, and then finally all my Z voltages. The voltage for my resistor is 64.8 volts. The voltage for my resistive component of my coil is 25.872 volts. Therefore, my total resistive voltage for my entire circuit is added together to become 90.679 volts. Since all these voltages are on the same phasor, they can all be directly added in order to get my total resistive voltage of my circuit. Keep in mind that right now, all I can do is measure the voltage across the resistor. That's the only one I can confirm with my meter. The next thing to do is figure out my inductive reactance voltage. So the inductive reactance voltage of my coil is the same as my inductive reactance voltage for my entire circuit because that's my only vertical value. So I have an inductive reactive voltage of 78.597 volts. Once I figured out these two, I can use Pythagorean's theorem again in order to find out what my total values are going to be. I already know what my circuit total value is at 120 volts, but I do need to find out what the voltage across my coil is. And this should be 82.746 volts according to Pythagoras. Now I can take my meter, I can measure the voltage across my resistor, I can measure the voltage across my coil, and they should add up to the same calculations I have here. Now that I have all my voltages done, I can now take those and start working on my power triangles. Remember that my power triangles should look exactly like my impedance triangles, and all the proportions should be the same. So to start with, we're going to find out what our true power is across all of our devices. Well, true power for my resistor, I can either use I squared times R, which is the more reliable calculation to use since I is my constant, or I can use V squared over R, and I should still get the same number, being 162.786. For my coil, I want to use the same formula, being I squared times R, and I get a total true power of 64.988. Once again, these are all in the same orientation, so therefore they add up. My total power of my circuit that I can measure with my watt meter should be 227.774 watts. The next thing to do is do my reactive power. My reactive power is only found in my coil, so therefore the reactive power of my coil is the reactive power of my circuit total, being I squared times XL, which is 197.425 bars. Lastly, I want to do my apparent power. I can get the apparent power from my coil as well as the apparent power from my circuit total. For my circuit total, I'll use E times I. Since E, my source voltage, was given to me and I is my constant, that's the most reliable formula I can use. I can still use I squared times Z, and it should come out to the exact same number anyway, being 301.425 VA. And I can also use I squared times Z on my coil to get the total apparent power of my coil as well. The last thing to do is just to figure out what my operating angle is going to be. So now I get my phase angle as well as the power factor. The easiest way to do this is to use my cosine formula, which is R divided by Z, which will give me my power factor. Inverse cosine of my power factor will give me my phase angle. you'll see that my coil is operating at a power factor of 0.313. My circuit total is operating at a power factor of 0.756. So the power factor of my circuit total, having that resistor in there, has actually a better power factor even though I've added a component. By adding a resistor with a coil, it actually improves the power factor. All right, so if you need to go through this video, because I know there's a lot of information in here, go through it as many times as you can until you feel comfortable. I have a worksheet waiting for you in Blackboard, so go ahead and check that out and then do the knowledge check before you continue on to part 2.